Air conditioning is great when you have it. Especially on hot and humid days like this one. But what about when air conditioning isn't an option? Well, that's exactly what we'll be looking at here today. A portable and rather energy efficient cooling solution. And you might think that I'm talking about this here. This is an evaporative cooler, sometimes referred to as a personal cooler or some other gimmicky name. Really, these are more properly referred to just as cheap junk. The actual thing that we'll be looking at today, this is a bucket that is partially full of water here. And essentially what this is a closed loop heat exchange system. So this is the heat exchanger that is set up here. Now the parts that I'm using are really more typically used for water cooling a computer or something like that. So not super industrial. To add some context to what we have here, this is all water that is basically wastewater. It's condensate from either portable AC or dehumidifier. So I thought, why not reuse it in some way before getting rid of it? So the way that I have this wired up, I have a simple 12-volt DC pump that it came with just some bare wires that I stripped and put in these wire nuts here that are then connected to this little adapter here. All of the 12-volt DC equipment I'm using uses 2-pin fan connectors instead of the more common 3 or 4-pin fan connector, which is what you see here. So I have a 3-pin to 2-pin adapter here. And then this is simply a 3-4-pin fan splitter with a switch so you can turn it on and off. And then I have another one of those adapters here. And then I have 2 fans that are plugged into this 2-pin fan splitter there. And then those go to these 2 fans that you see here. And all of this is connected to this switch, and then it runs off of 12 volts DC here, and that is just going straight to the wall there. So I'm going to go ahead and turn it on now. And you can see that water is now going into and coming out of the heat exchanger. And for the most part, it is relatively silent when operational, because even though it is a closed loop with water going back into the bucket, because the exhaust tube is submerged, you don't generally hear the water. Of course, we can take it out, and then you can hear it going back in. But if you submerge it, it is pretty silent. So right now we've been running it for, maybe about a minute or so, and already we have a 1 degree temperature drop. So up on top, you can see that is air that is towards the back, and the top of the heat exchanger, that is normal room temperature, 76.6 degrees. And at the bottom is air that is right in front of the fans coming out of the heat exchanger. The fans are actually in the back, but this is the cool side that cooled air comes through. And we can see that the temperature is dropping still. Alright, so it's been a couple minutes now, and the output temperature is currently 74.8 degrees. We're still at 76.6 up top. And of course, we notice the humidity is a few percent higher on the cold side, which makes sense because warmer air can hold more water. So we'd expect the relative humidity of colder air to naturally be a little bit higher, even if the moisture in the air is the same. Now, the important thing I do want to mention here is this solution does not add humidity to the air. It's not like an evaporative cooler which doesn't work in humid places in the summertime because it's increasing the humidity when what you really want to do is decrease the humidity. This is not releasing this water into the air. In fact, we can put the lid on this bucket to the extent that we're able, because this is a closed loop system. The water gets piped through the heat exchanger and then it goes back into the bucket. It's not going into the air. So we're not adding any water to the air, and if anything, if you have cold enough water, then condensation will start to form on the heat exchanger, so you might actually remove a little bit of humidity from the air. Now the other thing is the temperature differential is not huge to begin with here because this is room temperature. But we can do something more interesting here, like say turn on this dehumidifier that's sitting right behind here. So I've been running the dehumidifier for a little while now, and the temperature differential is about 5 degrees. You can see the dehumidified air is about 40% humidity, and on the front here we're seeing about 56% and about 80 degrees. Now some of this differential is just due to the fact that the dehumidifier vent is raised a little bit in comparison to where these sensors are. Now, the other thing I'll note is that I also have had the fans running behind the heat exchanger, but the water pump is not actually on right now. I've disconnected that. So we are going to connect that now. Alright, so I've connected it as normal now, and I'm going to turn everything on again. So once again, we have water flowing through the heat exchanger. And right now, we're about 85 degrees up there, and we just dropped to about 78.2. So just, literally just like that, the temperature went down 2 degrees, and now it's gone down another degree. So you can see that using a heat exchanger is significantly more effective when you have a greater temperature differential. Basically, you're going to get a lot more bang for your buck here trying to cool down something that's relatively hot rather than something that's room temperature. You're not going to be able to make as much of an impact there. So just like that, we're already down to 76 degrees at the front here, the temperature, and now we're down to 75.7. So another minute or so has gone by, and now we're at about 75.5 degrees at the front, 64% humidity. Again, the humidity we expect to be larger on the cool side simply because the temperature is colder. 75.3 degrees, and I expect at this point it's probably going to start stabilizing somewhere around 75 degrees. But this is still about 5 degrees cooler than we were prior to turning this on. I'm not going to claim the full 10 degrees of improvement simply because it was only about 80 degrees in the front before we turned this on. But we still dropped the temperature about 5 degrees. And keep in mind, this is using condensate water, but if we want to kick it up a notch, we can actually add some cooled water. I have a gallon of water in the fridge that we can add to this now and see what happens. So I have almost exactly a gallon of water here that I'm going to pour in. Alright, so I poured about a gallon of cold water in there, mixed in with the condensate water. Already the temperature has dropped another degree or so. We're down to 71.1. Wow, that was a big drop right there. The temperature just dropped 3 or 4 degrees just from pouring that gallon of cold water. And now we're at about 70.5 degrees, so we're continuing to drop a little bit. Let's see where we stabilize now. 69.9, so now we're below 70 degrees. We're 10 degrees colder than we were when we started, because I'm using about 80 degrees as our baseline since that's where we were at the front. 69.4, 69 degrees now, and we're still continuing to drop. 68.9. What the heck, I happen to have some ice here that we can put in here if we want to see what happens. So I'm starting here at 68.7 degrees prior to adding the ice. And I expect that's going to begin to drop again shortly here. 68.5. More thermodynamically inclined folks here might be wondering, well, this seems great, but nothing comes for free, right? Of course, you have to factor in the energy to run this whole operation here. And as far as what that consists of, again, all we've got is the water pump there, which is 12 volts DC, and then these two fans that are behind this heat exchanger. The heat exchanger itself is completely passive, so that doesn't need a connection. So we're running three 12-volt appliances effectively, these two fans, and that water pump. And what's the power usage of all that? Well, it's about 7.9 watts, less than 8 watts. 7.8 watts. So 8 watts, and we're dropping the temperature 15 to 20 degrees. Not bad. Now, as I said earlier, if the water is cold enough, condensation will start to form on the heat exchanger, and you can see that now. I can take my finger, and there's just condensation all over the ends of the heat exchanger here. Same with the other side here. Now, it's not so much that it's just dripping off the thing, but if you're running super cold water through here, that is something that you may want to take into consideration. Alright, so this is about 15 minutes later now, and as you'd expect, the temperature on the cold side has warmed up a little bit. It's only 71.2 degrees now, so this is still cooling, and still about a 10-degree temperature drop, but as we would expect, the temperature is steadily increasing now, but we still got some cooling capacity left, so we're going to continue to let this run. So it's been almost another half hour now, while I've been doing this and letting this run, I've also had an AC that's been running, and I've got a whole liter, a little bit more than a liter of condensate from it that I can add to the system and see what that does. Again, this isn't refrigerated cold water, it's just condensate, effectively wastewater from the air conditioning. And it looks like that's dropped the temperature a little bit and starting to go down now. So if you're running a dehumidifier or an air conditioner frequently, you may be getting enough condensate from it that you can use that to continually top up your cooling system. As the water warms up, you have new cool water that you can change that out with. It looks like we've stabilized at about 76.4 degrees. So that only resulted in a 0.7 degree temperature drop, but it was a liter of condensate that otherwise probably would have gone down the drain. So there's two things that I'm trying to demonstrate here. One is that if you already have a lot of this byproduct, this condensate that you're just dumping down the drain, you may be able to get creative and put that to use a little bit by pumping some heat into the condensate before you drain it. Thermodynamically, running the air conditioner or a dehumidifier just to get the condensate to do this is obviously not worth it. But if you're already running those appliances and you've got the condensate, then this effectively comes for free here. Of course, it uses about 8 watts. We're at 8.1 watts right now in order to run the system. But if your temperature differential is big enough, then that may make it worth it in your case. And secondly, you've seen how simple this system is. A lot of people, when they think about power outages and emergencies, they think they need a generator or something like that. Well, this is a system that you could easily run in a power outage to keep yourself cool for at least a few hours or some amount of time, depending on how much cold water you might have on hand. So if you have enough ice in the freezer, maybe a few gallons of cold water, that could be the difference between being able to sleep through the night in a power outage and not being able to. So this is a handy little system you can rig together for your own personal comfort for emergencies or other situations like that. Just run it off of a 12-volt battery pack or something like that, and you're good to go. So until next time, stay cool out there.